This video continues the discussion of analysis of variance. Last time we left off in chapter 12 talking about the step 4 and the distribution and the critical value and making that decision. But before we get to really looking at the F statistic and talking about steps 5 and step 6, let's talk a little bit more about the logic behind the F statistic. So essentially what we're doing is we're coming up with two different ways to estimate the variance in the population. And so the F statistic gives us some idea of how much overlap there are in our distributions that we're comparing. And so what we do is we can estimate the population variance based on between groups variability, and we can also estimate that population variance based on within groups variability. Now, if we expected the null hypothesis to be true, we would find that the variability between groups would be very similar to the variability within groups, and we would find that our F statistic might be somewhere around 1. So it'd be a low number if that between groups variability is less than or the same as the within groups variability. So again, here we're talking about degree of overlap. Here we've got three means that are fairly close together, and you can see there's considerable overlap among these three different distributions of scores. So in this case, we would expect to have a low F statistic. Here again, we're talking about the overlap of our distributions of scores, but those means are more spread out, even though they have the same variability. And so in this case, we might expect that we'd be more likely to find a difference among some of the groups. Maybe not the first distribution and the second distribution, but we might see a difference between the first distribution and the third distribution. But we'd have to do some post hoc tests to find that out for sure. In this last one, you can see that now, comparatively speaking, we have the same mean differences, but there's far less overlap, and it's much more likely that this mean would be different from this one, would be different from this one, because the distributions themselves overlap much less because the variability is less within each group. So the variability between the groups is greater than that variability within each group. So one thing that you will see commonly is called a source table, and it is giving you a breakdown of the source of variability for your analysis of variance. Is it a between groups set of variability? Is it a within groups portion of variability? Or is it the overall variability that we see? And what it does is it is a way to present fairly easily your calculations and what the final results are. And generally speaking, people can really understand a source table once they know what all the different elements mean, and that's not uncommon to be reported in the literature when you're doing analysis of variance. So here we have a source table, and what they've done is we filled in here what the different cells would be. So the first row is the between subjects source. The second row is within subject source, and then the final row is the total subject source. So we get the sums of squares between, sums of squares should sound kind of familiar. We are going to get to where that comes from. We also have our sums of squares within each group, and then we have the total sums of squares, basically ignoring group membership and using the whole sample instead of taking into account that people are assigned to different groups. Again, we have degrees of freedom between, degrees of freedom within, which we've talked about in the previous video, as well as degrees of freedom total. If we take the sums of squares between and we divide by the degrees of freedom between, we get the average squared deviation, and that's our mean squared between. We can also do the same thing with sums of squares within divided by degrees of freedom within to get mean squared within. Again, that's an average deviation for within groups variance. And then when we want to get the F statistic, we take our mean squared between divided by the mean squared within, and that will give us our F statistic. which is the thing we actually compare to that critical value. So here is another kind of way of viewing analysis of variance sums of squares. And what I've done here is I've plotted for each different type of cultural group where they have a foraging economy, a farming economy, a natural resource economy, or an industrialized economy. They participants participated in some sort of game in which they were given kind of control over how they can distribute any money that they have in this particular game. And so they looked at what percentage they would give to the other players in a particular game. And this we can see for foraging what that spread of scores are, again for farming, for natural resources, and for industrial. And you can tell that the levels somewhere, if we can estimate the center of each of these points, are going to be different. So if we wanted to look at calculating the total sums of squares, this introduces a new term for us. This new term is symbolized GM for grand mean. And what we do to calculate the grand mean is we basically ignore all of the levels of our independent variable, of which there are 4, and we just take the average of all of the scores, regardless of what group they're in. And that grand mean here is 39.385. Now the rest of this should look kind of familiar because now we have each individual score and we subtract out the grand mean. And we get some of the scores are below the mean and some of them are above the mean. We square each of those individual values. It's just like the first part of calculating a standard deviation. And we get the sums of squares total. And we can essentially say that the sums of squares is the sum of, here, let me show you right here. If we put the summation sign right in front of this, it's the sum of x minus the grand mean squared for each of these. That's what our sums of squares is. This is our sums of squares. Okay. So essentially what we're doing with that sums of squares is that we're saying, oh, well, what would be the variability if we just estimated it based on the mean of all of the scores? How well would that do? So we could draw this line across here and plot that grand mean, and you can see that some of them are pretty far off of that grand mean line. In fact, most of the scores are not very close, maybe perhaps this one. So the sums of squares total tells how far each individual score is from the grand mean. Now, if we wanted to talk about the within group sums of squares, right here, then what we would need to do is we would treat each one of our groups as if they were a single sample. So here I'm just highlighting that we have the foraging group. So I find the mean of these 4 scores, and that happens to be 33.25. And then I take it and subtract that mean, 33.25 from 28, and I get that deviation, and then I square it. And now I get to go and choose a different set of scores. And I'm just going to say here we've got the farming scores, right? This whole set of scores. And there's 3 of them. And we average those 3 scores right here. And we get 35.0. So now I'm going to take the individual score in the farming group and subtract out the mean of the farming group. So 32 minus 35 is -3. Square that value. And you do that for this next group. And then we might say, okay, well, perhaps we have this different set here in the natural resources, and we're going to do the same thing again. We've got the mean of the natural resource group, and we could subtract it out. You get -0.333, and then we have the squared value, and you would do that for each of those values. And then lastly, we have our industrial group. We find the mean again. We square, or we take and subtract out the mean from each score, and then we square those values. And then we sum them all together, okay? And that's what we get here is 166 47.419. So sums of squares within. So here's another way to kind of look at this, is to say, okay, each group gets to have their own mean as a way of calculating our variables. So what is it about knowing the spread within each group? How good of an estimate is that compared to the between group information, which we're going to get to in a minute. So you can see that these are probably much better than what we had before of that mean of 39 that ran somewhere around here. So the sums of squares within tells us how far the individual scores are from their respective group means. So now we want to calculate the sums of squares between. And you'll notice something interesting here, because now what we're doing is we're saying, okay, let's take the mean of each group, and I can circle them here, the mean of each group, right? And we got them all. And then we subtract out the grand mean. So we're saying, okay, we need to subtract out the grand mean here, and this is the grand mean right down here. Okay? So for each person in the group, each participant, we take the mean and subtract out the grand mean. So in this case, now we have 4 negative 6.135s. We square each of those. And so the between groups variability that's attributed to group membership now for all of the groups combined is taken into account basically because you're weighting it by the sample size. Because here we have 4 people, right? So we want to make sure it gets its fair share, and then we have 3 in each of the other ones. And so we're going to weight that information in the first one a little bit more. Then we take this mean here, the 35, and we subtract the grand mean of 39. We get our deviations, 1 for each person, square them. We do the same thing here. We take 47, subtract out 39, and we get our squared deviations. And then we do the same thing with 44 minus 39. We get our deviations and square them. And then we get our sums of squares between, so 461.643. So this would be another way of looking at it. So now I've plotted the means for each of our groups, and we're saying how far, weighted by the number of participants in each group, are these scores, the group means, from the overall mean of all the scores. So the sums of squares between tells us how far each group mean is from the grand mean. So here's a summary of our formula that we use. The sums of squares between, for each individual in a group, you would take the mean and subtract the grand mean. And you do that for every single group for the number of people that you have in the group, square those deviations and sum them together. We also have each individual score, and we subtract the mean and square those deviations for sums of squares within. You can also get the sums of squares total by adding sums of squares between and sums of squares within. But the other way you can get it to kind of check your values, you can add these two together and make sure that it's equivalent to each individual score, subtracting out the grand mean and squaring it. And you will get the same amount for sums of squares total. Okay, so now we have all the formulas in this source table. And this should also be listed in your textbook, so you can take a look at this in a little bit more detail. But you'll notice the sums of squares looks very familiar. It looks like the numerator of our variance. And the degrees of freedom between, if you get the mean square between, you take the sums of squares between divided by the degrees of freedom between, and you get the mean square between. So you can carry out those formulas. So here is our completed source table. You might want to pause a minute and see if you can fill in the rest based on the information in this video.